How do you build a glass dome big enough to house a mountain?
They really feel like a wonder of the world. There's nothing else like them.
What happens when a major station is completely taken apart and rebuilt during the rush hour?
This is like open heart surgery. The only problem is the patient is still jogging.
And how did engineers create the most outrageous building in all of Las Vegas?
You have to build something that gets attention. Your building is your billboard.
This is the age of the extraordinary.
Where else can you swim from one skyscraper to the other 300 feet in the air?
Where ingenious engineers have unleashed unchecked creativity.
Everything in this building pushes at the boundaries of what's possible.
Building structures so outrageous, they defy logic.
The forces on this thing look like it should be torn apart.
Now, their secrets revealed. Discovering the incredible stories of their construction.
These are extraordinary feats of engineering.
To try and understand, how did they build that? In the last 30 years, the Southeast Asian economic powerhouse of Singapore has seen its population double from 3 million to nearly 6 million. Finding the space to build here normally means building high.
The problem is, Singapore is a small island city, half the size of London, so space is at a premium.
When the government decided they wanted to give this booming population green space amongst the high-rises, engineers had to push the boundaries of what's possible. The end result was a solution packed with world firsts. Built on 1 million square meters of land reclaimed from the sea, 2 huge biomes, one the largest on Earth, engineered to keep visitors and residents cool in the searing tropical heat. Outside, a forest of giant super trees would be connected by a stunning skywalk, creating an avenue into the future.
Engineering doesn't get much more remarkable than Gardens by the Bay.
For the team that took it on, transforming a soggy patch of sand into an extraordinary state-of-the-art garden park would be the challenge of a lifetime. So, how did they build it? In 2007, work started on a huge new park for Singapore's residents. With over 80% of the population living in high-rise towers, it was desperately needed.
Cities need green spaces. Greenery absorbs carbon dioxide, it makes oxygen, and it just makes a city a more pleasurable place to live.
Working out where to build on this tiny tropical island was the first challenge that faced engineers.
You might well wonder how they found an extra 100 hectares in such a densely populated city. Well, they actually made it from scratch.
Today, Singapore is an island of 719 square kilometers. But a huge amount of the island's coast, the marinas, the airport, the industrial shipping ports, are actually built on land that has been created by the government. For the last 200 years, Singapore has grown by reclaiming land from the sea. But over the last 50 years, this process has accelerated, with Singapore now 24% bigger than the way nature intended. It was a 100-hectare parcel of this reclaimed land that meant the city could create a new green space. The plot, the size of 120 football pitches, was created in the 1980s by taking vast quantities of sand and rocks from building sites and seabeds and piling it up until it was above water level. This new land was then left to settle, but even by 2012, was still too soft to build big structures on.
The issue of reclaimed land is that you are effectively bringing in non-compacted gravel, non-compacted earth, and you can't really build onto that. And so what they did was actually put piles, long shafts beneath each of the foundations for the building structures they built, and they would extend down to the rock, to the base below the compacted earth.
These concrete and steel columns, firmly anchored to the bedrock, would be the key to supporting the two glasshouse structures. Now the architects and engineers could finalize the designs for building the park. It would be a project packed with innovation. Dominating the site would be the two huge biomes, or glasshouses, one with the largest unsupported glass roof in the world. Both would use a self-supporting latticework design with arcing beams to create the huge spans of glass covering 20,000 square meters of climate-controlled gardens. Outside, there would be a forest of man-made trees, reaching from 25 up to 50 meters in height. 18 super trees of concrete, steel, and plant life would be linked by an aerial skywalk towering over the groves below. The outdoor park would be planted with tropical species, which would thrive in the hot local climate. But the ambition for the two biomes was to house species from cooler, faraway lands. In Singapore, with its typical daily high of 32 degrees centigrade, that was a huge challenge. Glasshouses in cool climates work by using the glass to trap solar energy to heat up. This way, plants from much warmer climates can grow. Singapore's two biomes had to do something much more difficult. They had to somehow let in lots of light, but also stay very cool. Both needed to be around 25 degrees centigrade. But the huge flower dome with its plants from the dry Mediterranean spring climate of 4,000 kilometers north also needed to be very bright. With Singapore's humid, cloudy weather, the need for maximum light was the first problem the biome designers had to solve.
During the day, there's quite often a lot of cloud. The sunlight, it's not constant throughout the day, and it's not as much as the plants need to be able to grow. So we had to get every single ounce of sunlight we could into the conservatories themselves.
With daylight so crucial to the plants, the designers had to overcome the problem of how to support the huge roof spans without creating shade.
Most buildings need columns to stand up. It's how the load gets to the ground. But there is another way.
The solution to maximizing the light was to create a delicate curved framework to hold the 3,332 glass panels. Incredibly, this grid shell is self-supporting. It achieves this by mimicking an engineering design perfected by birds and reptiles.
A technique in engineering, an idea of using form and shape to provide the strength to the way a structure works. And you see it in nature all the time. An egg, for instance, is a perfect example of shape stiffness. The shell of the egg is a shell, and it's a three-dimensional surface, and it's very, very thin, but yet very, very strong. And that strength is created because of the form of it, the shape of it. And so we translate that idea into buildings.
By replicating the thin, strong, arcing structure of an eggshell, gravitational loads are evenly distributed down to the ground where it's fixed. The idea was a thin structure with no columns would allow in maximum light and self-support. But the huge size and that lack of supporting columns becomes a disadvantage when it came to actually building it.
Because we're creating this very large volume, there's a complexity in how the hell do you support it when you're gradually building it in stages, and obviously it all needs to be supported until it is the complete entity. A grid shell doesn't work until it's complete.
Engineers needed to work at heights of over 50 meters to assemble the roof structure. But a traditional scaffolding platform would have been complex and expensive. So instead, they came up with a simple but ingenious solution.
So they built a series of working platforms at substantial heights. So the lower, flatter, the Mediterranean biomes are around about 35 meters to the top. So building something as a working deck which was 25 meters and then doing a regular scaffold on top allowed a massive saving.
As the structure was completed, the grid shell should have been strong enough to support the glass by itself. But there was a potential problem.
Structures by the sea need to be especially strong. I mean, think about it. With all of the rain that can come in and wind and storms, they need to withstand all of that.
Winds of over 100 kilometers per hour have been known to hit Singapore. So extra strength was needed to protect the fragile grid shell domes. The answer was to crane in 28 radiating steel arches, which would stretch over the roofs. These arches were then bolted together, connected at their bases to a concrete ring beam, which itself was anchored to the deep piles driven down through the reclaimed land. Then they were bolted to the latticework frame. The domes could now absorb any high wind pressures and avoid a catastrophic structural failure. Now, it was ready for the glass.
In the conservatories, we have the arched ribs, which provide the resistance to forces which are sideways, which shells are not particularly good at resisting. So there we've got two things combined, the shell stiffness, the shape, and the arched ribs, which are very stiff horizontally.
The success of the two grid shells is clear, with over 100,000 healthy plants thriving inside, as well as plenty of light. They need a maximum daytime air temperature of 25 degrees, going down to 17 at night. But with the Singaporean sun burning down at midday, these glass houses would naturally heat up to well over 40 degrees. How have engineers prevented this from happening?
Greenhouses like to get hot. I mean, that's the bottom line. You know, glass is a great holder of heat, and the solar gain is trapped, and it's a really great thing in a cool climate. But in a hot climate, when you're trying to make something cool, is obviously a big challenge.
The first line of defense was installing spectrally selective solar glass. This deflects 35% of the sun's heat, but on its own, it wouldn't be enough. So the next line of defense is bespoke blinds that roll out when the sun is shining. Again, engineered to minimize impact when not in use.
The shading is tucked within the ribs and furls right back, like a roller reef sail, folds right back into the ribs, so it can disappear. Again, for the very strong principle that on a semi-cloudy day, you need as much light as possible.
Despite greatly reducing the solar heat coming in, the biomes would still get hot enough to kill the plants in a matter of days. The solution was building in an underfloor network of cooling pipes.
This is something that we had learned from the Northern Hemisphere. So in the Northern Hemisphere, they actually do ground heating. We just reverse the entire process and cool the slabs.
To ensure the cooling system is as energy efficient as possible, biomass boilers burn organic waste from here and gardens and parks across Singapore. This helps generate the electricity to chill the water.
It's extraordinary that the whole Gardens by the Bay only uses as much energy as a Singaporean office building.
With the structure completed, the next engineering challenge was building a mountain the size of a 10-story tower block inside. And working out how to build this 35-meter structure out of concrete and make sure its sensitive plants could not only survive, but thrive.
So for the mountain in the cloud forest, it is actually made out of, it is a typical concrete wall structure. So first of all, we have the concrete, and then We have a material called hypertufa. Hypertufa is basically a mixture of cement and soil to give it kind of like an organic material that will help.
Clever engineering helped these biomes imitate the natural world of thousands of kilometers from here. But outside, the designers took inspiration from the jungles that once grew here in Singapore. They created an extraordinary alien forest.
Super trees. They're exactly as advertised, basically like trees on steroids. Man-made, 16 stories high.
We were never trying to replicate a tree. We were trying to create a kind of modern 21st century version, an idealization of what a tree is in terms of using structures as steels and cables, but working in the way that nature does so, by being flexible and changing, and the way it supports nature.
These super trees aren't just steel and concrete, they've got plants growing on them, living on them. Somehow the designers have managed to incorporate a web of exotic plants into this man-made structure. All of these plants are incredibly heavy, so it's a fantastic piece of engineering there.
Rising between 25 and 50 meters into the sky, nothing like these super trees had ever been built before. With huge trunks and complex canopies, the engineers had to work out how to build them from scratch.
So what we tried to do was find a construction method which was repeatable. We build the cores, casting each of the pieces up one on top of the other, effectively using the same shuttering as you do in standard construction techniques. And once we built the concrete core, we then built the canopy on the ground.
To design the steel tree canopies, Neil drew on his experience building lightweight but strong staging for the world's biggest music acts, such as U2 and Beyonce.
What's interesting about the world of rock and roll and staging is they are willing to develop ideas, look at ideas, which the other part of the building industry would not.
That fresh rock and roll approach helped the team create a canopy that was light, flexible, and easy to install.
We built a scaffolding system, built the surface up around it, and then we lift the whole of the surface of the super tree canopy skin up to the top of the concrete core in one piece.
These incredible trees aren't just for looks. Some contain photovoltaic cells to generate power. Others act as chimneys for the biomass boiler exhaust fumes. And they all help solve another problem caused by Singapore's land shortage.
One of the main functions of the super trees is actually to allow us to showcase vertical greenery. So as a lot of people know, Singapore is land scarce. So the only way for us to continue greening the country is actually to go vertically.
The trees hold 150,000 plants, and the whole incredible forest is completed by the 128-meter skywalk, threading its way through the canopy, high above the ground.
The whole thing is built on land that was once the sea. It's got one-of-a-kind structures on it, and it's all powered by offcuts of trees. Pretty impressive, really.
It took 5 years for engineers to transform what was once under the sea into perhaps the world's most stunning man-made wonderland. The ultimate in human nature. It's always tough building in the center of a busy city, but imagine modernizing a crumbling old mainline railway station in the middle of London, while 1 million people a week carry on using it. That's exactly the engineering challenge that faced the team tasked with reinventing one of the oldest railway stations in the world, London Bridge, which by the start of the 21st century was also one of the worst. soon to be right below Europe's tallest building and hopelessly unable to cope with the demands of a modern city, something big had to be done.
This wasn't just a gentle reworking of the station. This was a complete rebuild.
The solution was a bold scheme to sweep away history and demolish hundreds of Victorian arches, creating a stunning modern concourse that connects everything like never before. Up above, tracks would be moved and raised with 15 new platforms built, all on polystyrene.
This is like open heart surgery. The only problem is the patient is still jogging.
50 million people a year, over 800 trains a day, and one ambitious transformational plan. So, how did they build it? Ever since London Bridge Station opened with its 2 platforms in 1836, it struggled to keep up with demand. As London grew, so did the station, but there was never a coherent plan.
London Bridge Station is 180 years old in places. It was built in 10 stages over that long period, which means that every little piece of that, every little stage is slightly different.
By 2008, London Bridge was very much the poor relation to London's other major stations.
It used to be impossible to find your way around. So easy to get lost in, a real mess.
Very muddled, very old, kind of hodgepodge of different styles. It really wasn't something like St Pancras. It wasn't built with one grand vision, so it was a very kind of down-at-heel station.
With plans for Britain's tallest building given the go-ahead, London Bridge Station was about to find itself next to the Shard. With another 400,000 square meters of office space, adding to the explosion of skyscrapers going up nearby in London's financial district, the station had to be able to cope with more trains and a lot more people. The problem was the site couldn't get any bigger.
Well, the ambition, first and foremost, was to get more capacity, more trains through the station, through the existing viaduct width, because, of course, London's been built up since the station was made. So we had no more width, we had to get more trains through.
All of London Bridge Station is elevated above road level. Its 15 sets of tracks and platforms fan out on top of a massive brick viaduct, 15 meters high and nearly 200 meters wide. Back in 2009, hidden beneath this viaduct was a massive warren of Victorian arches, which supported the tracks above. Most were little used and would make way for a huge new concourse. This was construction phase 1 and would provide the much-needed easy access to all the station's platforms above.
If you think of the concourse, we had a full section of Victorian arches, and essentially what we did was just cut a slice out of the middle of that, and we did that bit by bit.
Extraordinarily, the demolition all happened right under the working station. The network of arches underneath the 9 platforms and 15 railway lines were all interlinked and relied on each other for support. A 75-meter wide swathe of these needed to be demolished to make way for the new concourse. But first, to stop the arches on either side of the demolition area from collapsing, 2 huge concrete retaining walls would be built. With this in place, they would be able to bulldoze a 185-meter-long corridor through the arches and create a new space twice the size of a football pitch. This would become the all-new street-level concourse. Then huge new concrete columns would be built to support new platforms and tracks that would sit on top. These columns would need to support tens of thousands of tons of platforms, trains, and people, so they needed to be very strong and built to last. The construction team was managed by Adrian Tooth.
To support the amount of weight that comes down those columns, we have to drill what's called piles into the ground.
Inserting piles into the strong bedrock below for added strength wouldn't normally be a problem. But here, running right under the site, is the London Underground.
Some of our piles that we had, our 50, 60 metre piles right down into the ground to build our concrete columns, were really, really close to the Jubilee line. So what we had to do is, while we were piling, we had monitors on the tracks at the Jubilee line. So if the track started moving, we really knew we were in trouble.
With the concourse build well underway, the engineers now needed to figure out how to relay the train tracks that ran over it, while 200,000 people a day continued to use the station. On top of that, with the predicted rise in passenger numbers driven by London's booming economy, the rail networks wanted more trains to run through across London and fewer trains to terminate here. The existing track layout needed a complete rethink.
When we inherited the station, there were 15 platforms. So there were 9 terminating and 6 through. But to realise Thameslink, we had to change that to 6 terminating and 9 through. And that meant that every track in the station had to change position.
In order to achieve this switch around, the tracks all needed to be at the same height. But they weren't. The terminating lines were 2.5 meters lower than the lines with trains that continued on through, so they needed to be raised. But a big chunk of the track would still be held up by the 180-year-old Victorian brick arches, and these wouldn't take the weight of the concrete needed to raise the tracks.
So when we assessed the capacity of the existing arches, they could only take a relatively low load. So if we then needed to increase it by, say, 2.5 meters, if we had done that in something like concrete, you're adding a massive amount of weight to the top of those arches. So they weren't capable of taking that. So we had to find a new way of doing it.
They would also need to carry the weight of the new platforms.
They needed some kind of structural filler, something lightweight that could take the compressive load.
The substance they turned to was surprisingly simple and very common.
They used this, not a coffee cup, but the material it's made out of, polystyrene. The surprising thing about polystyrene is, although it's incredibly light, it's also incredibly effective when it's pushed down.
We built a foundation and then we put polystyrene wrapped in a plastic wrapping that has a 120-year design life. And then we built concrete around it that gave us the structure for us to get the tracks up to the level they needed to be, but it also was light enough so that it could sit on the arches below. So these are the kind of innovative solutions that we had to come up with, working on a station like this, where you have very, very old infrastructure next to very, very new.
The polystyrene itself is actually carrying a concrete slab, it's then carrying the platforms, and it's also carrying the weight of the trains.
Achieving all this and keeping the station open and safe meant taking one step at a time.
The complexity in undertaking demolition, building new platforms, canopies, while you've got trains running in and out is huge. What we did at the beginning was we took 2 platforms out of use. We would put the hoarding up, set up our work site. We would demolish those platforms and tracks and the arches beneath them, and then build up.
The new design and layout called for 6,000 meters of roof to snake over the new platforms. But the constraints of the site gave rise to yet another problem.
How do you build a new platform and a platform roof on site when you have no space to do it?
The answer is, you don't.
Various elements of the station build were prefabricated off-site. For example, some of the platform units and also the canopies were fabricated elsewhere and then brought into site. So the advantage that gave us was that it meant less on-site construction where we had limited space.
The platform canopies came in 3-meter-long modules and were put together like a DIY flat pack.
They came with all of the containment that carries the wiring within them. It came with cameras, speakers already set within them, all the lights were set within them. So it was just a process of putting one next to the other, filling in the gap between, and then wiring it all together. So very quick.
In just weeks, Each pair of tracks was raised, the platforms built, and the canopy completed. It required the different teams on site to work like clockwork.
You don't just have a designer making the design and handing it over to the contractor to build it however they want. They're thinking about the building process as part of the design. This is architecture meets engineering meets project management.
The teams also worked to ensure the historic Victorian features of London Bridge Station was celebrated alongside all the modern engineering. Like the 150-year-old columns, each supporting 4 connecting arches and the platforms above, many of these survived to become part of the new London Bridge experience. Where they couldn't be kept, they were mirrored in modern materials, but clearly defining the new from the old.
From an architectural vision perspective, it was important to repeat the historical importance of the original arches. So if you walk through that area, you'll see the original brickwork arches and then the new interpretation in board-marked concrete.
Thanks to the skill of architects, engineers, builders, and the rail company, the London Bridge Station modernisation finished on time in 2017.
This project was an amazing endeavour across all of the different disciplines. There was about 1,600 people worked on the project. In terms of numbers, I think there's 24 kilometres of platform edge that we put in.
We now have 10 times as much space as we did originally, so the journey that this station has come on is huge, and it's one that it's been great to be part of.
From being unable to keep up with even yesterday's demands, London Bridge has been readied for tomorrow, while retaining the best of its Victorian character. It took 8 years to reinvent this station as a shining beacon of railway efficiency. The ambition and achievement recognised with the prestigious award, Building of the Year 2019. In the beating heart of London, modern engineering and ingenious design has succeeded in creating a stunning station, fit to serve the city's travellers for another 100 years. Las Vegas, Nevada, where a gambler can take a quick tour of some of the world's most iconic structures before deciding where to splash the cash.
Every building is more extreme than the last, and it makes sense because this is Las Vegas. I mean, you have to build something that gets attention, and your building is your billboard.
Copies of famous landmarks might get you noticed on Vegas's main strip, but how do you make a big impression if your building plot is on the outskirts of town?
To get noticed in Vegas, they had to build something impossible.
But this was no casino. Here, a man was inspired to build a hospital so extraordinary it could also be a fundraising event space.
I said to my wife, Camille, if we're going to do this, we got to make a statement.
The result was a building almost as complex as the organ that inspired it.
There are 2 halves of this building. Just like the human brain, the left side is ordered and logical, and the right side is wild and creative.
This is the Lou Rouveau Center for Brain Health. Designed in California, engineered in Europe, fabricated in Asia, and built on 2 acres of Nevada desert. It's the show-stopping outcome of 65,000 hours of engineering effort, $80 million, and nearly 900 tons of steel. It doesn't look possible. So how did they build it? The building is the brainchild of American entrepreneur Larry Rouveau, driven to create it after experiencing the moment his father, Lou, was diagnosed with Alzheimer's disease.
I just said I would never want anybody to go through this humiliating, lack of dignity experience that I just went through. If I could ever do anything, I would change that.
Larry decided to build a new hospital for degenerative brain disorders. As well as being ideal for treatment and research, he also wanted it to be visually so extraordinary that people would want to hire it for events. To design it, Larry turned to one of the world's greatest architects, Frank Gehry. Aged 81 at the time, Gehry was very much at the top of his game, as one of his projects, the Guggenheim Museum in Bilbao, had recently proved.
The initial day he was here on this site, I told him what I wanted. He took out a yellow piece of paper and he drew it, and that's what I got.
A sketch was one thing, but Gehry already knew this building would be his most complex to date. So complicated, in fact, that only the world's most expert engineers would be able to pull it off.
Frank said to me, "So what would you say that if I told you this building, a building like this has never been attempted before? It will be engineered in Israel and India and Germany. And then it's going to be sent through the internet, the design, to China. And then we're going to ship it over here in 555 pieces, no two alike."
Budgeted to cost $80 million to build, the structure appears bent and twisted, as though it's collapsing in on itself. At one end, the extraordinary facade gives way to reveal a much more conventional building underneath.
Looking at the building overall, if you sort of divide it into two parts, the part with the sort of metal cladding, very chaotic and disorganized looking, that's our event center. The side where the medical care actually takes place is actually quite orderly.
The clinic building is actually a conventional 4-story white block structure, partially hidden behind the curving steel facade. But the south wing had an altogether different purpose, and so needed a different approach.
When we started out on the design of the building, I told Frank, most hospitals, most clinics, when they close at night, what happens? The janitors come in. Instead of janitors, I want ambassadors to come in. People will rent this building for weddings and events, and we live in Las Vegas. We could rent that out, use this as a revenue source to fund our research. So somebody can come here, rent this space, and feel good that they're helping a charity, and it's beautiful.
Gehry's vision for a must-see event space was a structure that was as jaw-dropping on the inside as it was on the out. The challenge for the engineers was to figure out how to build it with as few columns and straight walls as possible.
As you see, it is a huge structure without any support in the center. And the way it's manufactured in pieces, each piece, it varies from 2,000 pounds to 10,000 pounds, each piece. And they are made of steel, fabricated of huge pieces, from the size of a couch to the size of a car, almost.
The huge sections were heavy because the steel needed to be strong enough to compensate for the lack of internal supporting columns.
The amazing thing is that the curved panels on the building actually provide a lot of the structural support.
To achieve this, the panels needed to be very tightly bolted together. So engineers perfected a new way of connecting the frames.
It was designed on friction. The plates has to be tight against each other without air gaps. And that's the reason why we have to have so many bolts in each pieces.
But the construction team's problems were far from over. The people required to create these unique components were so rare, they were dotted around the globe. Dimensions were being calculated in Israel and India, then the parts being made in China. the builders on site needed to be sure they were bolting it together in the right way.
Just try and think about the level of precision that a project like this would need. If anything was wrong, they'd have to dismantle the whole facade and put it back together again. So the sequencing, the fabrication, and the construction were really key to making this work.
The answer was to barcode each piece of steel. Once the steel was on site and was offered for assembly, the individual barcodes would be scanned and transmitted to the main engineering team in Germany, who would cross-check to make sure the right pieces were being joined.
This system meant that every piece could be checked before it was slotted into place.
1/16 of an inch in one corner, off the other side, it would be a disaster. It had to be perfect.
Having worked out how to build the complicated steel frame, the engineers then turned their attention to the facade. Once again, architect Frank Gehry had a vision.
Frank said to me, since you're in the desert, I want the immediate impact. I'm going to use stainless steel.
But 1,800 curved stainless steel tiles on a building in a desert where the sun burns hot for 3,800 hours every year wasn't without its issues.
Stainless steel is super reflective. There's a risk that you'll get blinding light firing out in all directions, which is not what you want when you're building sitting on a major road junction.
The solution was a special angel hair finish applied to the steel. Micro scratches brushed into the metal with a stainless steel wire brush that helps diffuse the light.
That's what makes it absorb the sun instead of reflecting it as much. So it doesn't really shine in people's eyes.
With passers-by protected, the team turned their attention to making sure the light on the inside was also just right. Dr. Wint is in charge of patient care at the hospital.
The natural lighting, I think, is really important. It gives less of an industrial feel, and often that's important for some of our patients who don't realize they're ill.
Engineers installed 199 windows, allowing a lot of natural light into the hospital and event space. But you can have too much of a good thing.
Las Vegas is in the middle of the desert, so you're talking about some pretty high temperatures that can go as high as 40 degrees Celsius or 104 degrees Fahrenheit.
To protect occupants from too much heat and light, every window has blinds installed, each tailored and controlled by a central management system that's linked to monitors in the thermally reflective glass. It's this adaptability to harsh conditions outside and its sensitivity to those inside that helps make this building so outstanding. The best place for those most in need of a superbly engineered health center.
It is very unique and different and beautiful building, and somehow in a different way, very peaceful.
The Lou Rouveau Center took 3 years to complete and was the most complicated of Frank Gehry's designs yet for his engineers to build.
This building was exactly what I wanted it to be. It gave us the credibility. People knew we were serious. You want to build a Frank Gehry building for a disease, they know you're serious.
We built a building that you just cannot miss. You have to talk about this building when you pass by it, and hopefully people will also talk about what's going on inside. So I think for sure that part of the idea behind this building and its very unusual looks was to say, we are here, this disease is here, we're fighting it.
I love the fact that something that is housing work that's so important is also housed in a building that looks amazing as well.